So we're near the end of the semester right now. We've got like, what, 3 classes left or something like that? Not very many. We don't have class a week from today. Just have 1 class next week because of Pioneer Day. And so towards the end here, we get into discrete probability. And this is fun stuff for sure. So we're going to take a look at sort of when I say brief history, I mean really brief history, right? A couple bullet points. A basic definition of it, which we've already talked about what the definition of probability is, right? That equation. We're going to look at a bunch of sample problems because that's the best way to learn this stuff is to play around with it. Then we're going to look at complements and unions of events. So what's the probability of this or this event happening? We talked about that briefly the other day when I said, what's the probability of rolling a 2 or getting a face card out of a deck, right? That kind of stuff. We'll look at how to formally do that. And then we're going to talk briefly about this idea of probabilistic reasoning, which takes us to the Monty Hall problem. Who knows that problem? Anybody? You know about it? Okay, you don't get to play along since you know the outcome. Sorry. But you'll get to watch other people seeing it for the first time. It's kind of a little bit mind bender when you don't know about it. All right. So the origins of this stuff, it was originally developed to study gambling. That's why probability was invented, was created. And the book has some really good history and some of the people involved, and we're not going to spend a lot of time in that. But that is where it came from. Combinatorics and probability all is rooted in studying gambling. And if you ever take like an advanced, I don't know if, I guess if you're getting like an advanced math degree, something like where you're studying hardcore proofs and combinatorics and all these kinds of subjects that we kind of touch on a little bit, you learn about something called game theory. And I think it talks about game theory in the book a little bit. But you'll find that game theory and the study of mathematics as it relates to games, especially games of chance, it's everywhere. That's kind of where the foundations of it is. It's just fascinating to me. But this is another one of those things that, although it was developed, I think it was like in the 1560s or something like that, a long time ago, the concepts have moved forward and have been able to be applied to stuff that's in our modern world. Like in genetics, you can use probability theory to understand hereditary traits and things like that. Why does, when your parents, like one has blue eyes, one has brown eyes, what color of eyes are you most likely to have? That kind of thing. Or other traits, the baldness gene, all this stuff, right? Turns out the baldness gene comes from the mom's side of the family. Right, so it's the mom's dad, right? So my mom's dad, he was bald when he was like 19. It explains this, right? My boys are lucky because their mom's dad, my wife, her dad has just got a thick head of hair and he's in his 80s. But my daughter, all of her boys are going to get my baldness. Anyway, but I don't know if combinatorics and probability calculates that kind of thing, but it's similar. Those types of things, hereditary and those kinds of traits and those types of things. Interesting. Also, it can deal with helping you figure out algorithmic complexity, which is the entire subject of the 2420 class, data structures and algorithms, and we did touch on that a couple weeks ago. But there's a difference between what we call deterministic algorithms and probabilistic algorithms, right? So does anybody know what a deterministic algorithm is? You guys actually do know. You may not know that you know, but you know. Probably every algorithm you've studied is deterministic. It's one that just takes step 1, step 2, step 3, and it's always the same step every single time and nothing changes. Probabilistic algorithms, somewhere along the steps process, a random choice will be made, and it changes the outcome. And so what would that be useful for? Can you think of a scenario why you would want to have a probabilistic outcome or a probabilistic algorithm that would make a random choice somewhere along the way?
With a shuffle sort?
You could have you could, if you're shuffling a deck of cards, programmatically shuffling a deck of cards or just randomizing a list or something like that. You could, that kind of falls in that category. You can also use it to help calculate the average case of an algorithm rather than the best case or the worst case, right? We typically talk about worst case with big O notation, but you can calculate an average case by running a series of tests using probabilistic algorithms. So there's lots of different things that apply in computer science. And then it also helps us answer questions involving uncertainty. And this is where Bayes' theorem really shines, which we're not going to get into that for another couple of days. But the Bayes' theorem its foundation is probability. But it helps answer questions when we don't know all the details. And one of the ones I always use as an example is this email really spam, right? And you can answer that question with probability. You can't answer it for sure, right? That's why it's uncertain, but you can get a probability, you can get a percentage, you can get, yeah, it's 70% chance this email is spam, so I'm gonna block it. Or you can tweak the filter on your spam setting. Yeah, I only wanna block if it's 90% chance spam, or I wanna block if it's 10% chance, right? It'll filter everything out. But you can use probability and probability equations and Bayes' theorem and these types of things to solve these kind of problems. To me, that's fascinating. It's something that some gambler, the guy who invented it was a gambler. Laplace is a big player in the early days of it, and he was a gambler and a mathematician. But the other guy, they mention him in the book, and I can't remember his name right now, he was just a gambler. That was it. And he created all this stuff, combinatorics and not combinatorics, but probability to study gambling. And combinatorics and combinations, permutations, and all that stuff was also meant to study gambling. Just interesting to me. All right, so what is probability? We already know this equation, right? Number of successful outcomes over the number of possible outcomes. We've talked about this a couple of times. It's a simple formula. Really not that much to it. What gets tricky is figuring out what the top number actually is, where do we get it, how do we know what it is, and what's the bottom number. But we're going to formalize this a little bit so we can apply it in some multiple scenarios. So let's let E represent an event, right? An event would be, I'm going to roll a die, right? And I want to get a 2, right? That's my event, getting a 2. Let S be the sample space. So what would be the sample space in this scenario?
Only 1 through 6.
Yeah, 6 possible outcomes, right? It's just a regular die. Right? Wasn't a trick question. Yeah. So, yeah, exactly right. So, let E be the event that I want a 2, and let S be the sample space, which is rolling a 1 or a 2 or a 3 or 4 or 5 or 6 in a normal, regular 6-sided die. So that would be 2 over 6, or 1 over 6, which we'll see in a minute, okay? Because the event E of getting a 2, the fact that that's a number is a coincidence. Right? That's not the number we're going to be dividing, right? We'll see. So here's the formula. Probability of E, what do those little bars mean in our world here? Yes, the cardinality, right? Because E is a set. It just so happens that this set contains one thing in it at the moment, 2, because I want to roll a 2, right? It just contains one thing at the moment. But it's the cardinality of that set. Now, if I wanted to roll an odd number, 1, 3, or 5, well, then that set would contain 1, 3, and 5, and the cardinality of that set is 3. So that top number of our equation would be 3. Does that make sense? And then the sample space would still be 6, because the cardinality of a 6-sided die's possible outcomes is 6, all right? And the set S would be 6, or 1, 2, 3, 4, 5, 6, and its cardinality is 6 also. All right, so it makes sense? Notice that the set E, which is all of our events that we're looking for, is a subset of the sample space, right? It has to be, if you think about it. We're looking at what's the probability that I'll get this out of these different things, right? If I want to get a 3 or a 5 out of 1 through 6. Well, if 3 and 5 are not part of the sample space, the probability of me getting them is 0, right? I'll never get them because they're not part of the sample space. All right, so then this should be true, right? The cardinality of the events set will be greater than or equal to 0, right? What's the probability that I'm trying to calculate? I want to get a 1. Well, 1 is greater than one thing in my set. The number 1 is one thing, and that's more than 0 things. Now, maybe I'm wanting to get 0 things, right? What's the probability I'll get 0 things? Depends on what kind of a action you're taking, right? Okay, but that is a thing you could also get. But also note that the cardinality of the event set is either less than or equal to the cardinality of the sample space. Because maybe I want to know what's the probability that I'll get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Well, the probability of that was 100%, right? Okay, make sense? So this is our fun little formula here, right? 0 will be less than or equal to, less than or equal to the probability of any given event, which is also cardinality of the event set over the sample space, which will be less than or equal to 1. Do you understand why it'll always be less than or equal to 1? Right?
Not higher than 100%.
Yeah, you can't have more than 100% chance of getting something, right? Now, what this means is the probability of anything happening is between 0 and 1. There's no such thing as a probability of something happening being 1 point something, right? The probability of anything occurring is between 0 and 1. There's no chance it'll happen, or there's a 0.01 chance, or a 2% chance, or a 9% chance, which is 0.9, right? It's still less than 1. So this is an important thing to remember, that the probability of any event occurring is between 0 and 1, inclusively. And again, we're talking about finite sample spaces, right? If our denominator is a finite sample space, when we get into infinite stuff, we don't get into that in this class, so let's not even worry about that, right? All right. So any questions about the basic, this is just sort of what is it, what's the big picture, kind of what the formulas are that we're going to be working with. Pretty straightforward stuff, it's not too complicated, right? So we're going to look at a bunch of examples here, and we're going to make some assumptions. Assumption number 1, all of our items are fair, meaning this isn't like a loaded die or a weighted die or a coin that lands on heads 70% of the time, or two-sided coins or anything weird like that, or not two-sided. All coins are two-sided. Double-headed coins or double-tailed coins or anything like that, right? That reminds me, a friend of mine used to work in a magic shop, and people would come in all the time wanting to buy two-headed coins. They sold them there. But they would always say, do you guys have any two-sided coins? And my friend would pull out a regular quarter out of his pocket and hand it to him. It's like, yeah, there's a two-sided coin. And they would not process what he was doing. Yeah, there's actually a cool little sleight of hand thing you can do with a regular coin to make it look like it's got heads on both sides or tails on both sides. And so he would kind of mess with them and do that too. Anyway, funny. The other thing we're going to assume is that the sample space is finite, okay? So here's our first problem, first example. We have a box that contains 4 blue marbles and 5 red marbles. Simple enough. What is the probability that a marble chosen at random will be blue? That's the thing we're going to solve. We're going to start easy. We're going to get a little bit more intricate as we move along. But let's take a look. What kind of approach do we need to take here? What are some of the things we need to think about? I'll give you a hint. It's the same thing you always have to think about every time that you're doing a probability question. Sample space. What is that set, right? And what is the event, and what is that set, right?
So I have a question.
Yeah.
Oh, you probably cover it right now. So the cardinality, well, I understand that would be 2.
Of
Colors, marbles?
Oh, yes, yeah. If you talk, but we're looking at this, when we walk through this, you'll see. Yeah, I get where you're going with that, yeah. Okay. The reason it's not is because this red marble is not the same as this red marble, right? They are distinct individual items.
Okay.
Whereas something like the letter A, there's only one letter A, right? You know what I mean? If I had a set that had AAA in it, if it's a set, AAA that's just A. There's only one thing called A because sets don't care about this. But in this particular case, the 4 blue marbles are not the set, right? The 5 red marbles are not the set. The set, the event is me picking a blue marble, right? And there are 4 things there that I can do, right? The set is picking blue marble number 1, picking blue marble number 2, picking blue marble number 3, or picking blue marble number 4, right? Make sense? It's a good question, though. It's good to distinguish that. So in case you didn't catch what he was asking, when we talk about cardinality, if you were looking at the marbles as identical marbles and as that being the set, you could argue that, well, that's just the cardinality is 1. But we're not making a set of marbles. We're making a set of events. And those events are picking this marble, that marble, that marble, or that marble, right? Okay, good observation. So here's our formula. Probability of the event occurring is equal to the cardinality of the events set divided by the sample space. And what is the sample space? And let me see what my next slide looks like. Yeah, okay, what is the event set? Yeah, it's 4. It's the cardinality. And so this will be a little bit misleading here because I just put that E is equal to 4. But the cardinality of E is 4, right? There are 4 events that we could do. And then what is the set S? 9, right? There's because I can choose blue 1, blue 2, blue 3, blue 4, red 1 through 5, right? So 9. So we calculate it all out. It's 4 divided by 9, which is about a 44% chance of picking blue. Pretty simple. But the main thing I want to kind of drill home right now at the beginning of these examples is understanding this whole cardinality business with the set that we're involved in and understanding how do we figure out what those numbers are, okay? All right. Here's the next one. What is the probability that when 2 dice are rolled, the sum on the 2 dice is going to be 7? Okay, so again, we have to think about what's our sample size, right? 36, that's correct. Now, how did you come up with that? We have 2 dice, right? And there's 6 on each one. What rule is that? That's the product rule, right? For every roll of this die, a 1, I can roll 1 through 6 of the other die. And then if I roll a 2 over here, I can do 1 through 6, right? So I have, for every 6 rolls here, there are 6 rolls here. Using the product rule, using combinatorics, which is where that comes from, we get this. Okay, very good. What about the events? This one's a little trickier. We have to look at all the ways that dice can add up to 7, right? How many are there? Let's look at them as sort of ordered pairs, right? 1 and 6, that's an ordered pair, right? Those right there, right? Any others?
Do we have to account for 6 and 1?
Very good. Yes. We have to look at those as well. Now, why? Notice they are ordered pairs, so the cardinality of this is still 6, because 1 comma 6 or 2 comma 5 is different from 5 comma 2. Those are 2 different things. So the cardinality of this is 6 things. Why do I have to do 3, 4, and 4, 3? Yeah, it's because this die could end up as a 3, while the second die is a 4, but the first die could also end up as a 4, and the second die end up a 3. Those are different events, right? So our sample space we figured out is 36. Then our event space or event size, cardinality of the event set is 6. So we have this. And again, that E should technically be with the cardinality bars or the absolute value bars or whatever, but it's 6 events, right? Thus, the probability of any of those events occurring is 6 out of 36, which is about 16%. Okay? Make sense? Questions on that? Good? Okay, let's get into a little bit trickier ones. A lottery player can win a, quote, large prize when you pick all 4 matching digits in the correct order, right? So if the lottery numbers were 5, 10, 15, 20, the only way you could win is if you got 5 in that, you picked the first number being 5, the second number being 10, and so forth, right? So you can win a smaller prize if 3 of those 4 numbers match, okay? What is the probability? So what would the 3 of those numbers being the first 3, right? I think that's what the question's asking. What is the probability of winning a large prize and then of a small prize? Okay, let's look at the large prize first. What is our event set? What is the size of our event? Okay, here one vote for 4 factorial.
4-digit number, 1,000?
Say again?
1,000? Or no, it'd be 10,000.
10,000? Any other thoughts? So we got to use combinatorics to figure this out, right? So let's take a look here. The event is just 1. There's only 1 correct number, right? Whatever the lotto pick is, there's only going to be 1 correct number. Now, what's the sample space? That's 10 to the 4th. Why is the sample space 10 to the 4th? Say again?
There's 10 possibilities for each digit.
Yeah, we're essentially picking a 4-digit number, right? We're picking a 4-digit number here. It's just numbers 3, 9, 7, 8, or whatever, okay? And I may have misled you a minute ago when I said 10, 15, 20, because that would not be a valid pick in this particular scenario. These are digits here, okay? So yeah, there's 10 to the 4th because the first digit, there's 10 possibilities, 0 through 9. The second digit, there's 10 possibilities, 0 through 9. But the tricky thing is, what was the event? There's only one possible winning number, right? Now, what that winning number is changes every time they do the lottery, but there will always be one every time they do the lottery draw. All right, so it's just going to be 1 divided by 10,000. We all understand why? Yeah? And I guess I gave an explanation anyway, right? We talked about this just a moment ago, that there's 10 possibilities for each of those spots. I really should rely on my slides a little more instead of trying to wing it. All right, so there we go. The percentage is 0.01%. So the calculation comes out to 0.0001. I just turned it into a percentage. Very small chance, right? What about the small prize?
Would be 40?
For our event size,
Oh, well, no.
it's a little trickier. So are you talking about the event size or the sample size? Okay. I hear one vote for 10 to the 3rd.
Or,
Are we talking about the sample or the event?
I lost track.
Let's do sample first. Sample space.
It'd still be the same.
Same as what?
The large one.
Yeah, it's still 10 to the 4th, right? Because the whole idea is there's 4 digits that the lotto people pick, 2, 4, 6, 8, or whatever, and then we're trying to match them. Well, the only way I can win the large prize is if I got that exact thing, 2, 4, 6, 8. There's only one of those out of the 10 to the 4th possible ways I can draw out 4 numbers if I'm the lotto commission, right? Okay. So the sample size, you're correct, is still going to be 10 to the 4th, and I believe my next slide shows that without revealing what E is. Yes. See, I remembered. But what is our E? So how many ways can you pick 3 correct ones and 1 wrong one? That's what we need to figure out. This, again, is a combinatorics problem, right? And keep in mind, part of combinatorics is combinations, but part of combinatorics is also permutations and product rule and addition rule. Combinatorics is sort of an umbrella term for all that stuff. So don't get confused when I say combinatorics. It doesn't necessarily mean that it's going to be a choose problem. It may, a combination problem. It may not be. So how many ways can you pick the 3 correct and then 1 wrong? What does that look like? Starting here, the first digit, there are 9 wrong answers. Agreed? Right? So if the lotto picks were 2, 4, 6, 8, well, 1, 3, 4, 5, 6, 7, 8, 9 are where I would get the first digit wrong. Dig it? Okay, so using our product rule, one set is 9 times 1 times 1 times 1, which is just 9. But is that everything? Yeah, I could also get the first digit correct, but the second digit wrong, and then the 3rd and 4th correct, right? There's only one way for me to get the second digit correct. It's I pick exactly what they picked for the second digit, right?
Sorry.
Yeah.
Question. If you win the large prize, do you not win the small prize?
I think it's one or the other. Yeah. I don't, yeah. That's a good question to want to know if you're going to really figure this out for real. The question was, if you win the large, do you also win the small? And I think this is a problem from the book. I think the wording in the book was actually if you get only 3 correct, which would mean no, you would not win it. But that's a good observation as well, because you want to count, if that's the rule, that's a different probability, right? That's a different amount of money you're giving out anyway, okay? But does everybody understand why this first example here, we're not done calculating yet, but this is one scenario where I got 1 digit incorrect and I got 3 correct, right? So that's 9. Plus, I could get this pattern where the first one is correct, but the second one's wrong, and there are 9 ways to be wrong, right? It's everything but the number they picked. And then there's 3 and 4 are correct, and then of course there's this and this, right? So if you add all those together, then that is the total. So you're multiplying each little purple 4 set there with the product rule, and then you're adding together each different ones. So do you understand why that's an addition rule there? So I'm adding this total, which is 9, plus this, plus this, plus this. Dig it? Any questions about why that's the way it would go? Okay, that being the case, then 36 is our event size. And I just want to reiterate here on all of these slides, I made the mistake probably of referring to E as just the number, the cardinality, without putting the brackets around it or the lines around it. E is the event. What is the event? There are 36 events in that set, right? That's what that means there, okay? So our final answer is 36 divided by 10 to the fourth, which makes sense that there's a little bit higher probability that you can get 3 right and 1 wrong versus getting all 4 of them correct, right? So when you calculate everything out, you end up with about 0.36%. Not 36%, right? 0.36%. How we feel about that one? We good? So you see now, again, I want to just remind us, probability conceptually is simple. What you want to happen divided by what can happen. What you want to happen divided by what can happen. That's it. That's all there is to probability. The problem is, we're talking about counting. How do you count the number of things that you want to happen? Sometimes it's tricky, right? If it's rolling a die, I can just go, oh, I want that one, that one, and that one. That's 3 events. That's easy. But if I'm looking at something that's a little bit more involved, like picking certain winning lottery numbers, I have to use combinatoric principles, okay? All right, so far so good? Let's look at a trickier one. Some lotteries offer I was going to use the word ginormous, but I thought it was just a little bit unprofessional. But I'm not professional, so I should have used it. Some lotteries offer a huge prize for those who correctly choose a set of 6 numbers out of the first n positive integers. And typically, n will be somewhere between 30 and 60. So in other words, if n is 50, then that means that the possible choices are 1, 2, 3, all the way up to 50, right? So this question here, what is the probability that a person picks the correct 6 numbers out of 40? So I've given this, I shouldn't use the word sample because that means sample size, but what I meant there is, here's an example of a possible win. 5, 10, 12, 39, 23, and 2. That's a possible lotto number. So again, what's our E size and what's our sample size? What's our event size? It's just 1, very good. Our event size is just 1. Because it's, in this example I gave above, I have to get 5, 10, 12, 39, 23, 2 in that order to win. There's only one way to win, right? So E is 1. But what's our sample space? The whole idea is you're going to pick a number, the lotto commission people, the people who invent the lottery, they're going to tell you the numbers are anywhere from 1 through n. And all this is saying is that oftentimes n will be some number between 30 and 60. So it might be 1 through 30. It might be 1 through 31. It might be 1 through 32. It might be 1 through 49. It might be 1 through 59. It might be 1 through 60. Right? Does that make sense? Yeah. So it's anything in that range. So in our scenario, we're giving a scenario where they're saying 1 through 40. I have 40 possible numbers, and I'm going to choose 6 of them. Okay? That's it. 40, choose 6. Why did I use combinations instead of permutations? We were using permutations earlier. Why did I use combinations here? There's a key word in the first bullet point that should tip you off. Yeah. To win, you just have to get a set of 6 numbers, right? So my little sample win down there, 5, 10, 12, 39, 23, 2, that would be a set of numbers. It does not have to be in order. You just have to get those 6 numbers. Remember, combinations, order doesn't matter, which is why this is a choose problem, a combinations problem. 40, choose 6. If we were looking at getting that exact order, then it's a different calculation. But in this particular case, we just have to get those 6 numbers. But even that, look at how crazy the probability is, right? Because just get the 6 numbers in any order. That's it. I just have to pick the 6 numbers in any order. Well, when you have 40 choices every time, it's kind of messy. So we good on this?